So the idea with Faraday's law is that, well, we already know with Lenz's law that there's two things, right? That if you have a change in flux going through a circuit, you will have an induced current. The second thing that Lenz's law tells you is that is the direction of that induced current, right? That the direction is such that the induced magnetic field would oppose the change in the flux through the circuit. We know that, but so far we don't know how to calculate quantitatively what would be the strength of that induced current, right? So the question is, how much is the induced current? We know in what direction it flows, but we don't know how much it is, okay? So what Faraday's law tells you is that if you have a circuit through which there is some flux going, magnetic field lines going through it, and there is a flux through it, and that flux changes, right? What happens is that there is an induced electromotive force that appears inside the cable that drives the current in the cable, that drives the induced current. So if this loop has some resistance R, you can calculate the induced current in that loop because of the change in flux as Ohm's law would say, it is the electromotive force divided by the resistance of the loop. And that electromotive force, and this is the part of this is Faraday's law, is equal to the change in flux, the derivative of the flux with respect to time. So from Lenz's law, we already know that induced current has to do with change in flux, not just with flux, but with change in flux. This one tells you, well, actually, it is almost exactly equal to the rate of change of flux with respect to time, right? The only additional step there between this quantity, d phi dt, and the induced current is that you have to divide by the resistance of the loop to get the amount of current flowing in the loop, okay? This phi that I'm talking about is the total flux going through the circuit. But your circuit might be a coil that has many loops. Okay, so you have to be careful with that, because suppose that you had a wire that you wind like this, and that each loop here has an area A. And you put a magnetic field through this thing. What's the flux flowing through your circuit? The total flux flowing through your circuit, which is made of these two loops, will be the flux that goes through one of them plus the flux that goes through the other area, right? So that would be, if you had two loops, that would be 2BA. Now it makes no difference if you take these two coils and you fold one of them on top of the other one so that you get a neat coil that looks like this with two loops. If your coil has two loops, then and you have a magnetic field going through it, then the flux going through that coil is going to be 2 times BA. N, because you could have 2, 3, 4, 5, whatever number of loops that you have in your coil, your total magnetic flux is going to have to go with N multiplied by the area of one of the coils times the magnetic field that is flowing through this coil, right? So that's important, because when you're using this equation for a coil, right, you'll have to stick in an N there, d phi dt, if your coil has more than one loop, right? Let's look at this example here, which is in your book, of an application of Faraday's law. For the case of a solenoid, as you can see there, a big solenoid there, and there is a ring there inside the solenoid, and the solenoid has a current that changes with time as described by the plot on the bottom. So the current on the solenoid starts from 0, it ramps up linearly all the way to 10 amps, and then once it reaches 10, it stays constant. The question is, what's going to be the induced current in this loop, in this ring inside the solenoid? Okay. So you have all the parameters there. The little ring has a 2 centimeter diameter. The solenoid is 20 centimeters long and it has 1,000 turns. The diameter of the solenoid, which I don't think you need, is 4 centimeters. And the direction of the current flowing in the solenoid is, I don't know if you can see that, but if I were to draw that there, it will be like this. On the top, maybe a different color. It's coming out of the cables on the top, and it's going into at the bottom. Okay, that's the direction of the current in the solenoid. So that is the current that is plotted at the bottom as growing initially between 0 and 1 is growing. So what is the flux? In what direction is the flux going through the ring? The problem is already helping you by telling you that the magnetic field inside the solenoid is pointing in the direction of the blue arrows. Right? And you can confirm that if you do the right-hand rule. Put your thumb in the direction of the current coming out, and your fingers are going to be inside the solenoid. Your fingers are going to be pointing to the right. So that is the direction of the magnetic field of the solenoid inside. So the flux through the little ring there is going in the same direction. And according to the plot, that flux is increasing, right? So you would expect that that flux is, because the current is increasing, the flux through the ring is increasing. And then you're going to have an induced magnetic field that points in opposite direction to that, and that will tell you the direction in which the current is going to flow in the ring. But what I'm interested in here is in finding a numerical answer to the induced current inside the ring, not just to figure out in which direction it's flowing. Right? So for that I need Faraday's law, which says that the induced electromotive force in the ring is going to be equal to the number of coils of the ring only has one, so that's going to be 1, but it could be more than 1, times d phi dt. This is the flux that is going through the ring. Now what's the flux going through the ring? The flux going through the ring is equal to the magnetic field that is going through the ring multiplied by the area of the ring, right? The magnetic field that goes through the ring is due to what? Is the ring generating its own magnetic field? No, it's the magnetic field of the solenoid. So in these problems, be careful with that. That's an easy mistake to make, to get confused about which B you're talking about. This is not the B induced that I'm using to calculate the flux. It's the B of whatever external object is putting a magnetic field through your circuit. So this is going to be the B of the solenoid. And you're going to have to multiply that by the area of the ring. Now, how is that flux changing? The flux through the ring, how is that changing? Well, B, the magnetic field of the solenoid, is increasing. How do we know that it is increasing? At least initially. Because the current through the solenoid is increasing. And we know that the magnetic field of a solenoid is connected to the current that flows through the solenoid. There is an equation for that, right? We use Ampere's law to find that equation, for example, if you remember. So that equation turns out to be this: mu sub 0, the number of turns of the solenoid, the current that goes through the solenoid, divided by the length of the solenoid. Okay? So if the current grows, the magnetic field of the solenoid grows. If the magnetic field of the solenoid grows, the flux going through the ring is going to grow also. If the flux grows, there will be an induced EMF in the ring. So that's the logic for this problem. Right? So now you just have to replace all of these quantities in the upper equation. So let's do that. So the induced EMF in the ring, it's going to be the number of turns of the ring is just 1, so I'm not going to write that. And d phi dt, well, d phi dt is the derivative of the magnetic field of the solenoid times the area of the ring. The derivative of the flux is going to be the derivative of the magnetic field because the area of the ring is not changing. So that will give you the induced EMF equals dB dt, that's dB dt for a solenoid, multiplied by the area of the ring. Now what's dB dt? dB dt of the solenoid is, I use this equation, I take the derivative on both sides, the left and the right, So on this side, I get dB of the solenoid dt. And on this side, the only thing that changes, well, mu is a constant, the number of turns doesn't change, the length of the solenoid doesn't change. The only thing that changes is clearly the current that is flowing through the solenoid. So instead of the current, I'm going to write di dt. Right? Now what's di dt? That would be the slope of the plot that you can see there. The current between 0 and 1 second grows linearly. It goes from 0 to 10 amps. So the di dt is equal to 10 amps per second. Every second the current goes up by 10 seconds in that interval of time. Right? So I have this di dt, which is going to be equal to the slope of this thing right here, and that is 10 amps per second. So I take that number and multiply by this constant mu sub 0, n of the solenoid divided by the length of the solenoid. That will give me dB dt. Once I have dB dt, I stick it in here, multiply by the area of the ring, and that's your EMF. That is the EMF, the electromotive force that is driving the current in the ring. The current in the ring is simply that number, the induced current in the ring will be simply that divided by the resistance of the ring, which is given in the problem as 0.01 or something like that. Okay? So that's how you would tackle these kind of problems. Again, be careful with the n that goes in Faraday's law. The induced goes with an n if you have more than one turn in the coil that you're using that is getting a current induced. So it's the n times d phi dt. So the current has a certain value that will be the result of your calculation between 0 and 1. But after 1, di dt turns 0. So di dt is 0, therefore the induced EMF on the ring is going to be 0. Therefore the current, the induced current is going to be 0 after t equal 1 second. Now the direction, let's take a look again at the direction just for practice. Let me look at the solenoid from this point of view. From the left. I'm looking at the solenoid from the left. So what I see is the solenoid, which is this circle, and it has current flowing this way. This is the current of the solenoid. And that current is growing. So the flux through the ring, and the ring is going to be placed inside the solenoid. The flux through the ring is going, as you can tell, is going in. Everywhere inside the solenoid there is a magnetic field going like this. This is the B of the solenoid. And that is going in and is increasing, at least between 0 and 1. So that means that the induced current is going to go in what direction? Delta phi goes into the page, right? So that means that the induced magnetic field on the ring should be pointing out of the page, right? So the induced, this red now is B induced. For a coil to have a magnetic field that is pointing out of the coil like that, the current will have to flow this way. This is the direction of the induced current. So on this diagram, the current goes up on this side and goes down on the other side to oppose the changing flux, which is going to the right and is growing.